Hey guys, in this video we're going to talk about three different elementary flows, uniform, source, sink, and doublet. The main idea behind these elementary flows is that they are all solutions of Laplace equations, and if we add them up we will get some pretty interesting shape that kind of looks like what you see in real life. Okay, so I hope you all saw the video before on stream function, potential function, and Laplace equation. If you have not seen that, I strongly recommend you going back and seeing it. Even though you think you may know what those are, there are there is always a small benefit for you to go look at those videos, right? So that you have a good flow of thought, flow of information connecting from the previous video to this one, right? So as we talked about in the last video, the elementary flows are basically the flows that were developed to simulate objects, to flow over different objects. Okay, so the first elementary flow is basically the simplest form of flow that you can model using math, which is the free stream, right? So before that, I strongly recommend you guys to also look at and print the handout on elementary flows. So that elementary flows handout should look something like this, right? It's there. I kind of gave you, pretty much the guided notes that I give out in class. So please make sure to download these, and if we can print them out, that would be great. Okay. So getting back to the slide. So as we discuss these every single elementary flows, I want you guys to go to the handout and then basically follow through the derivation. If you're if it would really help if you actually look at the handout first and see if you can go through the process and then come back to it, and then watch the video. Okay. All right, let's get to it. The first elementary flows, as I said, is the simplest form of flow that you can model, which is the uniform flow. And we know that the velocity vectors for these are, u equals v infinity, which means there are, it's a constant velocity, right? And small v equals 0, which means there's no component in the y direction, right? No component in the y direction equals 0. So if you are able to determine the stream function for this, I really hope you guys did that in the handout. Remember we talked about u equals dou psi by dou x, u equals dou psi by dou y, and v equals minus dou psi by dou x. Using those formulas, you can actually determine the stream function for the free stream, which is v infinity times y, right? So I would ask you guys to develop the stream function equation for a free stream with a given angle of attack. Say, for example, if you have a flow coming in at an angle, say that angle is alpha, right? What would be its stream function? Because you need to know how to model the flow coming in a different angle to simulate the flow over flow over an object at different angles of attack. So this is something you're gonna code anyway. So might as well do it now, right? In any free space in the handout or in your notes, just go through and derive an expression for stream function equation for a flow coming in at an angle of attack alpha. All right. So I'll leave that as an exercise. So the second elementary flow is what is called the source and sink flow. Okay, and as you can see, it's very easy to represent those flows in terms of radial coordinates. So before we look at the equation, you just look at how the flow, look at the flow itself and how, what kind of flow we're trying to simulate. So in the source flow right here, right, it looks like the flow is emerging from a single point. Okay, and looks like most of the velocity is in the radial direction, and the tangential direction velocity is basically 0, right? And if the flow is emanating from a single point, then we call that it's a source. If the flow is kind of converging to a single point, then we call that as a sink. But the only difference it takes is that for a source your strength will be positive, and sink the strength will be negative, right? Now let's look at the equation. As we saw that there's no tangential component, So your v theta is 0, right? Now we're just left with VR, which is the radial component. So let's look at, it's given by, this lambda divided by 2 pi r, right? So lambda is called, it's kind of, you can think of it as the strength of the source and sink, which basically represents the amount of mass coming through a single point or mass going in to a single point, right? So what this says is that VR is proportional to this capital lambda, or the strength of the source. That means if the strength of the source goes up, you get more mass and more velocity coming out of a single point, right? And you can also see that the velocity is inversely proportional to the radius. All that says is that as you move further and further away from the center, or your velocity will actually go down. Okay, so there are gradients with respect to VR, right? So that's the mathematical representation of the source sink flow field. Okay, so again, in polar coordinates, we know that VR equals 1 by r dou psi by dou theta, v theta combined to dou psi by dou r, right? Again, don't disregard the polar coordinates, because time again we will basically come back to polar coordinates because in some cases it's just easier to work with, right? So, but again, in terms of plotting, we'll convert to Cartesian, but in terms of analysis, sometimes polar is easy. Okay, so all we're trying to do here is trying to develop a stream function equation psi for this flow field, source and sink. Okay, now again, I leave it as an exercise in your handout to actually determine, before you go along this video, pause right here and see if we can determine the stream function equation for this flow field. Okay, all right. So now I hope you guys developed an equation, and if you want, you can check in this step that you actually got the right equation. Okay, so all right, simplifying these two equations and integrating, you should pretty much get the stream function as lambda by 2 pi times theta right here. Okay, now here you have a stream function, but we like to work in Cartesian space because it's it just makes it easier to plot, in my opinion. So we know the conversion for polar to Cartesian, right? There's a nice command in MATLAB you can do, or you can just follow the simple the transformation, which is r equals x squared plus y squared. All this if you're unfamiliar with this transformation or Cartesian polar to Cartesian conversion, all this is representing a single point in xy space. Say for example this is x and this is y, so you can represent this point as x comma y, or in terms of r and theta, right? So that's pretty much you're looking at the same thing, same 2D space, but from a different frame of reference. Okay, so again, x equals r cos theta, y equals r sin theta, r is square root of x squared plus y squared, and you put that in and you basically get these, right? So theta is tan inverse, correct? Because when you take the ratio of this, you get tan inverse y by x. Now you see there are two different terms that pop up, or variables x naught and y naught. What do you guys think these x naught and y naught is? So if you're thinking it's the location where you place the source and sink in the Cartesian space, then you're correct, right? So this allows us to take the source and sink and move it anywhere in the Cartesian space that we want. Okay, so basically now you have a stream function equation. Woohoo, right? Now, what do you need to do if you need u and v velocity vectors? Well, we know the stream function equation for all of these, right? U equals dou psi by dou y, v equals minus dou psi by dou x. So when you do that, you actually get u and v, which is pretty cool, right? So, right, here is a MATLAB function, which actually, moving forward, you'll have to rely on MATLAB, the differential commands that are in there for symbolic differentiation. So, I kind of gave you a code as an example. So you program the psi function, and then you basically do, differentiate with respect to y, you get u, differentiate with respect to x, you get v. Basically, that's your u and v velocity, right? But when you're working with the numerical values, make sure to use A10-2 instead of A10, because again, A10-2, tan, the inverse tan takes different signs in different quadrants, as you know, right? So tan is positive in the first quadrant, tan is negative in the second quadrant, it's positive in the third quadrant, and negative in the fourth quadrant. Okay, so if you don't do A10-2, then you will have some issues with the sign. Okay, so just make sure to use A10-2, not A10, when you deal with numerical values. Okay, so that's pretty much source and sink elementary flows. Now let's watch what happens when you actually combine these two. You can check for yourself, whether or not they are solutions of Laplace equation. Okay, they are. So, but what's more interesting is to when you put them together and see what happens. Okay, you will get a flow something like this, right? So I did this I did this like back in 5 or 6 years ago in an online solver called Ideal Flow Solver. So you can, I think it still works. You can go, just type Ideal Flow Solver and you can get, but you really don't have to, because you're gonna program this anyway. So, and you'll get to play, you get to see how things change, how things, how velocity and pressure changes across a given flow field, in the next homework. So, right. So basically, all we have here is that now we have the equation for the stream function equation for uniform flow, stream function equation for source sink flow. We add them up, and these are solutions of Laplace equations. So the addition will also be a solution of Laplace equation. So then all we're trying to do is you differentiate with respect to u and v, and with respect to x and y, and you actually get u and v. Now this is your velocity vectors components, in a flow field, right? Which is pretty cool. So when you do that, here, this is sort of the flow field you end up getting. So here is the location of the source, and here's your free stream. As you can see, because of the strength of the free stream, the radial velocity components that are emanating from the source gets pushed out, by the free stream. So you'll get kind of this shape. Now think about this. For the free stream, flow is coming this way, right? And we know that the velocity increases as you go in the radial direction, well, to a certain point, and then it gets an inverse relation with respect to radius, but initially it starts out at a higher velocity and then it slows down, right? So at some point along this line, these two velocity vectors are going to cancel each other, and the net velocity will be equal to 0. Now you might think about it. Where do you actually expect the velocity to go to 0? So velocity goes to 0 in a stagnation point along the surface of the object, right? So that means if you were able to find where the velocity goes to 0, then you track the streamline that is going through that point, and you will actually get the shape of the object, which is pretty darn cool if you think about it, right? So all you're trying to do, again, you're just basically matching two different made-up flows, and in the end you get something that resembles flow over an object. Now that shape looks like the front of like a nose cone of an airplane or a shuttle, or any other, or a smoother bullet or something, right? So it sort of, you can see that the streamline goes around the object. It doesn't intersect or do anything. More importantly, watch what happens to the distance between the streamlines. All right? Watch what happens to the distance between the streamlines. As it goes around the curvature, it goes down. Remember when we talked about the different theories of lift, that we really don't have a universal answer for why the velocity is increasing around a curvature? A lot of people have a lot of theories, but there's no universal consensus on what makes the flow to accelerate around a curvature, right? But this simple mathematical tool allows us to see that the flow accelerates when it goes around the curvature, which is again, it's pretty cool. It gives us a method to understand what's going on in a flow field, and now we can understand what the flow is doing around an object. Even though it's an inviscid case, it tells a lot of really neat information, right? So that's the beauty of it. We just started with absolutely nothing, right? We made up a bunch of flows, and then in about 15, 20, about 30-minute time frame, we actually got something that resembles what you see in nature, right? That's why the topic of aerodynamics is so interesting. Is that you can do some pretty cool things with just not a lot of stuff, right? So moving on, this type of shape is actually called a Half-Rankine, and you'll get to simulate all of these with in the next homework. So basically, you have the shape right here. Remember that you can only identify the shape if you find the stagnation point. Okay, because if you don't know where the stagnation point is, you cannot find the surface of the object. Okay, so once you find the surface of the object, then you can pretty much negate all the streamlines that are inside that surface, right? So again, on the right, you have the velocity vectors. So as you can see, the flow comes in from left to right, and then kind of goes around the curvature, right? So again, pretty cool. So we also talked about the sink flow, right? So what happens if you put a uniform flow plus source plus sink, right? We know these are all the equations right there, right? The only issue is that if you're putting source in a different location than the sink, okay? So that's why it is very, very, very important for you to include the center location of the source and sink. Okay, so we subscript to, right? Otherwise, if you place it on the same plot, if you put a sink on the same point as a source, you won't get anything. They'll cancel each other out. Okay, so what you're doing is, you're putting source. This is the stream function for the source, and then this is the stream function for the sink. Just make sure that the stream function for the sink flow basically has a negative lambda, right? So to generalize, I just left it like that, but stream function for sink has negative lambda. Now you can understand, you have the stream function again. If you want u and v velocity, you guys know what you have to do, right? You program this equation in MATLAB, find the derivative of this with respect to x and y, and you pretty much get this equation right here. Now, as you can see, the equations are getting more and more complicated, which is why you need to rely on MATLAB to do symbolic differentiations. Okay, you can't do this by hand, and don't try to do this by hand. It's not worth your time. You have the tool, right? Might as well use it. So when you do that, and when you put source and sink on the different locations, you will get something similar to what you see in real life. This shape is kind of an oval shape called the Full-Rankine, and you can actually see that there are two stagnation points now instead of one, and those stagnation points lie, at this location right there. So we'll talk about how to find the stagnation points in the other, as we move along in this video, but that's integral to this process, right? Without finding stagnation point, you can't find the surface, right? So you got to look for them and you got to find them, right? So again, how neat is that? You get something that looks the flow around in a cylinder, or not quite a cylinder, kind of squished cylinder, like a Rankine. But this is where you get to be creative, right? So move the source locations. I think my source is placed somewhere in here, and my sink is placed somewhere in here. Okay. So start moving the source and the sink. See what happens, right? Now think about this, right? What happens if you increase the strength of the source, right? And use smaller compared with smaller strength for the sink. Or sink is basically this way, right? What do you think happens to the shape? Yes, you can imagine the shape sort of like converges, 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 something like this, right? Now, can you see where this is going? You get something that resembles an airfoil, right? How cool is that, right? So again, we started with absolutely nothing. Now we are very close to simulating flow over something that looks like an airfoil, which is pretty cool. And not only can simulate the flow field, you can actually get the velocity vectors around it, right? That means at each and every individual location, you know what the velocity is, which is, again, which is a holy grail of aerodynamics, right? So you can do that within the confines of your ability, with just this information presented in the last two videos alone, right? Okay, that's, to me, it's pretty darn cool. Okay, so again, you'll get to do all this in the next homework, which is, again, I hope you enjoy it because I had a blast. So we'll do this elementary flow, and then we'll talk about the fourth elementary flows, which is the vortex flow, in the next video. All right, so doublet flow is sort of, it's made up of source and sink, but there is a condition. Okay, so imagine you have a source flow on one side and sink flow on the other side, separated by a distance L. Okay, so as you can see, these are the stream functions, right? These two are the stream functions. Now, doublet flow is basically you're bringing these two close to each other, but keeping their strength as constant. Okay, so it may seem odd a bit, but now think about it. When you bring these close to each other, when they lay on top of each other, they cancel each other out. So there's no point in doing that, right? So what we're trying to do here is we're bringing these to each other, these two source and sink close to each other, so that the product of the strength times distance stays constant. Okay, so basically bringing, again, close to each other, again, that's a condition. The product of the strength and the distance is a constant. Okay, and we call that a kappa. So kappa is, it's sort of like the strength of the doublet, right? So in the handout, I kind of walked through some of the steps that I skipped in here. Basically, that kind of shows how you can get from this step right here to the stream function, and basically this step right here to the stream function. But that's nothing. As you go through the handout, you see that the steps are pretty well laid out. So if you have any questions, just let me know. Okay. Again, we have a stream function equation for a doublet flow. Again, we like to work in Cartesian space because it makes it easier to plot. This is basically the steps I was mentioning. So I'm not going to go through it in this video, but if you have any questions, just ask me later. Right? Basically, we have this stream function equation. Then we convert to Cartesian. You end up getting the stream function in x, y, s space. Now, again, you guys know what to do to get u and v, right? Put it in MATLAB, and you actually get the expressions for u and v, which is pretty cool. Right. Now, let's watch what happens, right? Just like how we superimposed uniform source and sink, we're going to superimpose uniform and doublet flow, right? And in the end, the result is basically flow over a cylinder, right? Which is, again, pretty cool. So flow over cylinder, again, you have the free stream component and you have this doublet component. Please make sure to keep the y0 and x0 in there, because that'll allow you to change the location of the doublet. Okay. Now, one thing to note in doublet is that it has a sense of direction to it, right? So, you can make the doublet. You can see that there are like two rotation circles right here, right? So there's top and the bottom. These have a sense of direction to it. So that means if you want the direction to pass, to go from left to right, what that means is that your flow is actually rotating counterclockwise in the top direction and then clockwise in the down part. So if your net kind of the sign for the doublet is like this way, it's negative, that means that it's positive. It's the top part is rotating clockwise and the bottom part is rotating counterclockwise. So when you superimpose streamline and the uniform plus the doublet, make sure that these two kind of the direction of the doublet is opposite to the direction of the free stream, so that you get that stagnation point that you're looking for. Okay, so here you sort of have the equation for the combination of source plus uniform plus doublet. Again, you get flow over a cylinder. Again, for the first time in aerodynamics, people were able to simulate flow over a cylinder using just the concept of stream function and elementary flows, right? Which is again in the Laplace equation, which is this is very important. So this is what we are trying to do. Remember, towards the end of the last video, we saw that we cannot just take the equation of a circle superimposed with a free stream, but we can make up what is called this doublet flow, superimpose that with a uniform flow, and you get a cylinder-shaped circle, or a cylinder-shaped object, right? And you can determine the velocity variations, and from there you can determine pressure using Bernoulli's equation, right? So before we end this video, I'm going to show you just, I just wanted you to think about how you can find the stagnation point in the cylinder, because I highlighted this surface of the cylinder, but you can't really do that without finding these stagnation points, right? So how do you do that? All right, let's start with the stream function equation. You guys know that's your U and V, right? Don't copy these equations to your code. Just do the diff commands, because you got to use the x naught and y naughts as well, right? So how do you find the stagnation point? It's pretty simple if you think about it, right? At stagnation point, your U and V should be 0, right? So set them to 0, right? To make things easier, let's assume that the y coordinate of the stagnation point is 0, because it lies in the y equals 0 line. Okay, so let's just assume the y coordinates of stagnation point is 0, so that means y equals 0 and u and v equal to 0. If you basically solve for it, solve for x, you will get x equals square root of minus kappa by 2 pi infinity, which is pretty much the radius of your circle, right? So when you program this, make sure to note the stagnation point equals to minus kappa by 2 pi infinity, right? So now you can simulate flow over cylinder of different radius, and only thing that you have to change here is the kappa, really, right? Because when you increase that, as you can see, I mentioned before that the doublet has a sense of directionality, right? So that's why your kappa has to be a negative. If it's positive, then you get a complex number, right? So when you input kappa, it needs to be pointing towards the free stream, which is the negative direction. Okay, so make sure the kappa should, it's negative, but really controlling the magnitude will let you increase the size of the cylinder, right? So that's pretty cool. So we'll continue from this in the next video. All right.